So what I'm going to do now is going to demonstrate how to configure the common fork join pool using a couple of different techniques that we've talked about. And this is going to be demonstrating the code that's shown in the EX20 folder in my GitHub repository, which of course you can always get in open source format. In addition to demonstrating how this works, we're also going to understand the performance impact of configuring the common fork join pool size. So, as I mentioned before, you can control the size of the common fork join pool programmatically through several different means, as we just talked about. This particular demo is going to show how you can use the ManagedBlocker to add new worker threads to the common fork join pool. The way this is going to work is we're going to have a method here called test download behavior. And as you can see here, it's going to take a function, which is an abstract interface. It's a functional interface that's defined in Java 8 and beyond. And we use this to pass different strategies for downloading and storing images from remote websites. So this is using our good friend, the strategy pattern, which you undoubtedly have learned in other courses that you've taken at Vanderbilt if you took the 3-251 course. So what we're going to do here is we're going to use this strategy, this function strategy in a parallel stream. And when we run this thing, we're going to see we have some different results based on different factors. So this particular program was run on an earlier laptop I had that had 12 cores. My current laptop has 16 cores, so we'll see if that makes any difference in performance. And as you can see here, it's going to go ahead and run 3 different strategies. The first is just a default behavior that'll download and store 42 images using the 12 threads that were in the pool by default. And then the other 2 models are going to use this ManagedBlocker mechanism we've talked about to adaptively increase the size of the common fork join pool. And so it's going to download, these other 2 models will download 42 images using 43 threads in the pool, because the pool is going to be expanded as the program runs. And you can see when we actually run the program, which we'll do in a minute, that the results show that the versions that used the adaptive behavior perform better. And the reason for that is they're blocking less of the time. Now, as always, your mileage may vary. And so when we run this program in a second, we may get different results, but this is how it works in this particular context. So let's go ahead and take a look at the code. So here's the code for the program. I'm going to walk through this code. This is the EX20 folder. And this example is going to show how to combine Java parallel streams, both with and without the fork join pool ManagedBlocker interface and the Java fork join framework to download multiple images from a remote server, which happens to be running here at Vanderbilt, but not anywhere near me. It's 20 miles away or so. So let's take a look at the program. It's got a main entry point, which parses the command line arguments if there are any passed in, and then it creates an instance of the EX20 class and runs that instance. So here's what it does. The run method, which is what's called here, goes ahead and prints out how many processors the execution environment thinks it has access to, which on this computer should be 16 because I've got 8 hyper-threaded cores. We then go ahead and warm up the common fork join pool just to make sure it's got all the threads allocated to avoid perturbing the later results. So we want to be able to get consistent behavior. And then we're going to make 3 calls to the run test method. We'll look at run test in a second. Run test is the main driver method here for this test. And we're going to pass in 3 different strategies. One's called download and store image. One's called download and store image MB for ManagedBlocker. And one's called download and store image BT for blocking task. So those are the 3 different strategies we're actually going to use for this particular program. So as you can see, there are 3 different ways of being able to run these tests. So let's go ahead for kicks first and just run the program and see what kind of results we get. And the first thing you can see is that when we run this, it thinks that there are indeed 16 cores available because I'm running it on my 8-core multi-threaded MacBook Pro. And it should be cranking away here doing the processing. And I'll tell you what, let's just start it up here so it can run. Some of these images are rather large, so let's let it crank away in the background. and we'll keep talking about the rest of the tests. Here's the run test method. You can see that run test takes in the download and store image function, which, as we saw up here, can be one of these 3 different strategies. And what it does is it first does some garbage collection, and that just makes sure that everybody gets to start with all the memory allocated for it, so we don't have differences in performance because the garbage collector had to run in the middle of one of the tests. We then go ahead and time the following test. So the run timer.timeRun is this helper class I've shown in previous lessons, where this will go ahead and time how long it takes to do this particular computation. And what we do here is we're going to call the test download behavior function, passing in the download and store image strategy, and that will then go ahead and do the work. So here is test download behavior. You can see what test download behavior does is it first deletes any loaded images, and then it goes ahead and gets the list of URLs we want to download, which is provided by the options singleton. And then we convert that list of URLs into a parallel stream of URLs. And then we use the map intermediate operation to download and store each image in parallel. And then the final thing we do here is we collect the results up into a list. So we end up with a list of images, which are the files that we downloaded and stored. And then we go ahead and print out how many of these were downloaded. So it'll tell us, in this case, there should be 42 of them. So that's basically the test driver behavior. Now let's go ahead and take a look at the different implementations of these strategies. So if you recall, there are 3 strategies. There's the download and store image MB for ManagedBlocker, and download and store image BT for blocking task. So here's the first one. This is the one that just does download image. And as you can see, download image just makes a new image, and it downloads the content from that URL. And here's download content. Download content simply takes the URL, opens the URL, and then reads the contents at that URL, a buffer chunk at a time, and then stores it, and will end up returning that as a result. So this will come back here as an array of bytes, which we then use to convert into an image. So we make an image from an array of bytes. So that's what download image does. You can see it just blocks. There's nothing fancy schmancy about this at all. In contrast, here is download and store image MB. And download and store image MB for ManagedBlocker is a lot more clever than download and store image. And in particular, what you can see here is we're going to use the ManagedBlock method defined on the fork join pool. And what we do is we make ourselves an anonymous ManagedBlocker implementation here. And this is going to have a block and an is releasable method. And the one that matters here is the block method. This is defined on the ManagedBlocker interface. And what it's going to do is this block method is called automatically by the framework, by the fork join pool framework, if it's not able to get the object, get the contents without blocking. And of course it can't, because it's going to have to download it from a remote server. So what it does is it also calls download image, just like we called up here, except the difference in this case is by calling ManagedBlock, that will tell the common fork join pool to make a new thread and add it to the pool temporarily, while this call blocks. So a new thread will be created. So we're going to end up with more total threads by using the ManagedBlocker mechanism. So this is one way to do things. Now, the downside with this approach is it's kind of ugly writing this code. We had to do an anonymous inner class, and therefore we had to do this clever, probably sort of sleazy trick by making ourselves an array with one element in it in order to be able to have a side effect, just kind of crufty and ugly. So the third and final approach here to implement a strategy for downloading and storing images is to use this implementation. This is download and store image BT for blocking task. Blocking task is a little helper class we'll take a look at. And this helper class has a static method called call in ManagedBlock. And what you do is you pass it a supplier lambda, which in this case is just going to download the image, and call in ManagedBlock does all the magic necessary in order to do the managed blocker without requiring all this kind of ugly anonymous interclass nonsense. So let's go ahead and take a look at call and manage block. Here's blocking task. Blocking task basically implements this clever suggestion that's provided here in this Stack Overflow article, which I highly recommend you take a look at. It's a very, very good approach. Not without its flaws, but it's pretty cool. And here's the call and manage block method. It's static. It's parameterized by type T, where type T is going to be the type of the supplier that's passed to it. So in this case, it's going to be an image. And so, or let's say in this case, it's going to be URL. And so what we do here is we go ahead and we make ourselves a local variable called of type supplier managed blocker. We'll look at that in a second. And that essentially encapsulates the supplier that's passed in here. And then we say fork join pool manage block, and this particular parameter is going to encapsulate the managed blocker interface. And assuming that all goes well and no exceptions are thrown, then we're going to get the result from the managed block that we passed into the managed block method on the fork join pool. So let's go ahead and take a look down here to see what the supplier managed blocker class looks like. This is a nested private static helper class. And this is what implements the common fork join pool's managed blocker interface. And by doing this and encapsulating that within the managed blocker class, we no longer have to write this gobbledygook code here and do all these sleazy things with one element arrays and so on. So instead, here's what it looks like. The supplier managed blocker class has a supplier as a parameter, as a field. It has a result field. It has a done field. Its constructor just tucks away the supplier into the supplier field. And then here's where all the fun happens. This is the block method that gets called back automatically by the underlying fork join framework for the managed block method. And this will get the result of the supplier, which in our case is going to go ahead and download that image. And then we go ahead and set that into the result field, indicate that we're finished, and return true. And then get result just returns the result. So what we're doing here is we're making a little helper class called essentially blocking task, and blocking task is then used to encapsulate all the managed blocker mechanisms, and therefore our code gets really simple in order to be able to use the managed blocker mechanism. Okay, so given that, let's go back over here, and you can see what happened with our processing. And as I had shown you before, here's the number of threads in the pool. We started out with 16 threads in our pool. So test default download behavior only used 16 threads, whereas these other versions used 43 threads. And when we execute this thing, you can see that the managed blocker mechanism was the fastest, kind of as I had anticipated. And that's because it's using more threads. But as I mentioned also, your mileage may vary. So we're running over a network here. I'm going from my house where I'm teaching the class back up to Vanderbilt while I'm also trying to do a streaming, a live stream of the underlying mechanism for Zoom. So there is some perturbation. But in general, you'll find that the managed blocker mechanisms work better because they've got more threads at their disposal. So that's the end of our demo that showed how you can use various mechanisms like the managed blocker interface and the encapsulation of the managed blocker interface in the form of blocking task in order to be able to provide a more adaptive way of increasing the number of threads that are used in the common fork join pool when a program runs, when it actually knows what its needs are going to be in terms of blocking behavior. So that should give you a better idea of what you can do if you want to learn how to program these things yourself. And this is particularly important because a lot of people don't really understand that you can use the common fork join pool for blocking operations. It's a common misperception that the fork join pool and the common fork join pool are only good for compute bound or compute intensive operations that never block. And that is not correct. And the reason it's not correct is because they have this cool ManagedBlocker mechanism in there that allows you to use these features, and then the system will auto-scale the use of threads. The fork join framework will auto-scale the number of threads it uses in its worker thread pool in order to make sure that things can make forward progress even when other threads in the pool are blocked.